Good morning to one and all. In this video, we are going to discuss about bending stress by using K method. I am Dr. Ganesh M, Associate Professor, Department of Aeronautical Engineering, Hindustan College of Engineering and Technology. Outline: bending stress due to symmetrical bending stress due to unsymmetrical bending, methods to find the bending stress, and K method. Bending stress will produce when the section is subjected to bending, whether it may be symmetrical or unsymmetrical. Bending stress is denoted by sigma b. Bending stress due to symmetrical bending. We know bending equation is m by I is equal to sigma b by y is equal to E by R, by where m is equal to bending moment, I is the moment of inertia, sigma b is the bending stress, y is the distance from neutral axis, E is the Young's modulus, R is the radius of curvature. From the bending equation, if we rearrange the first two terms, sigma b can be written as m by I into y. By using this equation, we can find the bending stress due to symmetrical bending. Bending stress due to symmetrical bending. If the vertical load is applied, sigma b is equal to m by I into y, where m can be calculated as mx is equal to Vy by IL, where when the vertical load Vy is applied on a cross section, where sigma b can be written as mx by Ix into y. Bending stress due to symmetrical bending. If the horizontal load is applied, sigma b is equal to m by I into y, where m is equal to m can be replaced as my is equal to Vx into L, where Vx is the horizontal load. So from the horizontal load we can find the moment about y, my. From my we can find the bending stress sigma b is equal to my by Iy into x. Similar way we can find the bending stress due to unsymmetrical bending. If the incline or vertical and horizontal loads is applied at the same time, we can find the bending stress sigma b is equal to m by Ix into y plus my by Iy into x. But we cannot consider when both the load is acting at the same time, so we cannot take mx by Ix, my by Iy. So instead of that, we have to consider Ixy of the section. Methods to find the bending stress: K method, principal axis method, and neutral axis method. So here we are going to discuss about the K method. Let us consider an unsymmetrical section, cross section. So here we have considered x-axis, y-axis. X-axis is the horizontal axis and y-axis is the vertical axis, x and y. So let us consider a small moment about x-axis mx and moment about y-axis my. So due to these two moment mx and my, let us consider a small element of cross section area dA, which is at a distance of vertical distance and horizontal distance x and y. So where x is the horizontal distance and y is the vertical distance from x axis and y axis, and this F is the force acting on that small element. So from the basic equation, sigma z, that is bending stress on the cross section, sigma z can be written as k1 into y plus k2 into x. So let us take this as equation number 1. Df is equal to sigma z into dA, where dF is the small force acting on the small element, and sigma z is the bending stress acting on that small element. dA is the cross section area of that small element. From this we can find the shear force acting on the small element. If you want to find the forces for the whole section, F is equal to integration of a to 0 sigma z into dA, where if you want to find the moment about x-axis, mx can be written as F into y, that is force acting on that element into vertical distance, that gives the moment about x-axis. Similar way, you can find the moment about y-axis, my. My is the force into perpendicular distance here is the horizontal distance, where so F into x is the moment about y axis, my. So that you can take as equation number 2 and 3. Substitute 1 in 2. Equation 1, that is sigma z. In equation 1, mx can be written as integral of a to 0 k1y plus k2x into dA into y. From this, if you separate these two terms k1y and k2x, so we have the equation integral of k1 dA y square plus integral of k2 dA x. So k1 and k2 are the two constants, so you can take out of the integration, and we have this k1 integral of y square dA plus k2 integral of xy dA, and integral of y square dA can be written as ix, integral of xy dA can be written as ixy, where ix is the moment of inertia about x-axis and ixy is the product moment of inertia. This you can take as equation number 4. In similar way, we can substitute 1 in equation 3, we can get my, and similar way we can substitute sigma z in equation 3, we can get this. Yes, first we want to separate the terms k1 and k2, and k1 and k2 are the constants, we can bring out of the integral and substitute. Instead of integral ixy, integral of xy dA can be written as ixy, and integral of x square dA can be replaced as iy, moment of inertia about y-axis, and moment of inertia, product moment of inertia ixy. So this you can take as equation number 5. So now we can solve equation 4 and 5, we can get k1 and k2. So first equation number 4 and equation number 5, by multiplying equation number 4 into ixy and multiplying the equation 5 by ix, so we have the equation. So we can add these two equations. So when you are adding this, these two terms are cancelling, this term k1 ix iy and minus k1 ix iy can be cancelled, and remaining we have mx ixy plus my ix is equal to k2 ixy square minus ix iy. So from this we can find k2 is equal to minus mx ixy plus my ix divided by ix iy minus ixy square. Similar, this you can take as equation number 6. Now you substitute 6 in equation 4 or 5, you can get k1. K1 is equal to my ixy plus mx iy divided by ix iy minus ixy square. This you can take equation number 7. So once you can substitute k1 and k2 in equation 1, you can get the bending stress for a unsymmetrical bending. Sigma z is equal to my ixy plus mx iy divided by ix iy minus ixy square into y minus mx ixy plus my ix divided by ix iy minus ixy square into x. So this is the bending stress equation of a symmetrical bending as well as unsymmetrical bending by K method. Thank you for watching this video.